Yeah, good morning. So in the last class, we have discussed about the mapping theorem, and today we discuss about the Nyquist stability criteria. Nyquist stability criteria. So here, the Nyquist has used the mapping theorem. He has used the mapping theorem, and he developed a criteria. He developed a criteria to study the to study the stability of the to study the stability of the any control system in a frequency domain. So the Nyquist used this mapping theorem and developed a criteria to study the stability of any control system. So, and he has suggested that to select a single valued function, that is, which we have told in the last class, that is f of s, which is equal to 1 plus g of s into h of s. So he has to select, so he has suggested that select this single valued function, which is 1 plus g of s into h of s, where this g of s at h of s is nothing but open loop transfer function. It is nothing but open loop transfer function. So, and he has also given in the last class we have discussed about pole zero configuration. So if we discuss the poles of 1 plus g of s into h of s is equivalent to poles of g of s into h of s. That is, we can call it as open loop poles. Similarly, what are the zeros of 1 plus g of s into h of s, which we can call it as, is equivalent to the closed loop poles of the system. But here we know this will be known because we know the g of s into h of s. We know the g of s into h of s will be known. So based on this g of s into h of s, we can find out the open loop poles. But in this, when you are these zeros of 1 plus g of s into h of s, these zeros of 1 plus g of s into h of s will not be known. So the zeros, we don't know where it exactly located. Where is exactly it located? But for the stability point of view, when I'm talking about for stability point of view, all the zeros of 1 plus g of s into h of s must be in the left of s plane. So it has to be lie in the left of s plane. So all the zeros should be lie in the left half of s plane, we can say. So then we can say the system is stable. So no zero should lie on the right half of the s plane. Right half of the s plane means this is called right half, and this is called left half of the S plane. So all the zeros has to be lie in this left half. Then only we can say the stable system. So it should not, any zero should not fall on the right side of the S plane. So we are studying this stability by analyzing where the zeros are lying. So from this what we can say is, so we are studying the stability based on zeros, where these zeros are located in the S plane. So what Nyquist has suggested is, rather than studying this what you call all zeros on the left hand side, rather than studying the all the zeros on left hand side, so examine, or it is better to test the presence of any one zero. If any one zero lies on the right side of yes plane, then you can say you can say the system is unstable. So rather than studying all the zeros are lying on the left hand side, so that we can say the system is stable. So we study only if at least if any one zero lies on the right side of the S plane, then we can say the system is unstable. So studying whether all the zeros are lying on the left hand side or right falling, so then only we can say the system stable. So rather than studying the stability, so study for any one zero is falling on the right hand side of the S plane, then we can say the system is stable. Now, and also he has suggested that tau of S path which has to be encircled, because we are studying the right side of S plane as we are studying the right side of S plane. So Nyquist has suggested, so choose the tau of S path. Choose the tau of S path which starts from plus j infinity. Say this is plus j infinity, and ends at say minus j infinity, which covers the entire right half of plane, right half of S plane. So it means that it has to start from plus j infinity like this, and it has to go like this, and then like this, then it has to end at this point by closing this right half of S plane entirely. So it means that the whole right S plane. See, this is the S plane. So right side of S plane, it is covered by this tau of S path. This is, we can say, tau of S path. So Nyquist has suggested, because we are studying on the right hand side, so this right hand side to be covered, that for total right hand side of this S plane has to be covered by this Nyquist plot, I mean tau of S path. That is what he suggested. So this is studied from, that is plus j infinity to minus j infinity, and also it has to be continued first like this along the imaginary axis, then it has to end, I mean close this path exactly where it started, exactly where it is started, with the radius of infinity. So if you take the radius of the circle, r is equal to infinite, so encircling the total, if I say r is equal to infinity, then it covers entire the right side of the S plane. So this path is, we can say it is Nyquist path. This path is called as Nyquist path, which we have chosen, that is from plus infinity to minus infinity, that is which encircles the total right side of the S plane, is called as Nyquist path. And we need to analyze the stability of the system by using this Nyquist path. So now, if you take the as poles of G of S, H of S, we know poles of G of S into H of S, we know that is nothing but poles of 1 plus G of S into H of S. That's what we have discussed. That is poles of 1 plus G of S into H of S, we know. So we know the value of P. We know the value of P is nothing but number of poles, which is a poles of 1 plus G of S into H of S. Number of poles which are encircled by Nyquist path, which are encircled by Nyquist path. So here, this P is defined as number of poles which are encircled by Nyquist path. So now map all the points on the Nyquist path into F plan. So mapping theorem, use the mapping theorem, and map all the points in this S plane onto the F plane. So use the mapping theorem, and then transfer all the points onto the F plane, onto the F plane. So transfer all the S points onto the F plane. That's what we discussed in the previous class. That is mapping theorem. So this mapped locus, which are done by using the mapping theorem, that mapped locus which are obtained in the F plane, So this is S plane. So this is, if you look at here, this is S plane. So this S plane, what are the points here? If you take on the imaginary axis as well as on these points, and all these points has to be converted into a F plane. So all the points has to be mapped to the F plane. So this mapped locus which you have, use the F plane in obtained in F plan, which are called as Nyquist plot, So Nyquist plot is nothing but after finding out this right side of the S-plane Nyquist path. This Nyquist path, which is in the S-plane, has to be taken all the points and mapped to the F-plane. So that plot is called as Nyquist plot. That plot is called as Nyquist plot. So here, as we know that locus of this S-plane, locus of this plane. So by using that, we need to find out how many number of encirclement that is of origin, which you are going to take by Nyquist plot in the F plane. So here the number of encirclement has to be find out. That is number of encirclement which you have discussed. This how many number of encirclements of this path, about the origin. So this n is nothing but of origin in F plane, not S plane. It is in the F plane. So we need to find out how many number of encirclement is there. So based on that, n should be equal to satisfy this condition. N is equal to z minus. This condition has to be satisfied. Once we find out the number of encirclements of origin, we know the number of zeros, the number of poles. So here n and p we know that. We know from this n is obtained from the F plane. N is obtained from the F plane. And then P is also known from G of S into H of S, as we know that open loop transfer function. Then we can find out the Z. Z is nothing but here. A number of zeros of this is nothing but 1 plus G of S into H of S function which you have taken, right? Zeros of 1 plus G of S into H of S encircled by Nyquist path. So we need to find out Z is equal to by using this equation. So Z is number of zeros of 1 plus G of S into. So when I say it is encircled by Nyquist path, so with the Nyquist path is on the right side of S plane, right side of this. So we are going to study that Nyquist path encircles only the right half of S plane. We know that right side only it is covered. So it means that the number of zeros are lying on the. We are studying that number of zeros lying on the right hand side. So what is the stability statement for absolute stability? For absolute stability, Z value should be 0. Okay, so the fragile no zeros should be lie on the right hand side. That is what our intention. So then only we can say the system is stable. If any 1 0 is lying on the right hand side, then we can say the system is unstable. So by using this, if it is Z is equal to 0, the number of encirclements is equal to minus P. So from this we can conclude. This. If Z is equal to 0, N is equal to minus P. So Nyquist stability criteria says. So this is the important conclusion which we need to draw from this. So Nyquist stability criteria states that for absolute stability of the system, the number of encirclements, N is the number of encirclements of new origin of F plane, number of encirclements of new origin of F plane. We are talking about here F plane, right? So that is F plane, which is by Nyquist plot, must be equal to the number of poles of equal to the this P stands for number of poles of 1 plus G of S into H of S. So it should be the number of encirclements should be equal to the number of poles that to be in clockwise direction. So that the encirclement can be taken place in the clockwise direction. Why clockwise? Because the negative sign. Because of the negative sign, we say this is about the clockwise direction. It has to be taken. The number of poles of 1 plus G of S into H of S equal to number of encirclement is equal to number of poles, and that to be the encirclement is we need to discuss about the direction also. That is why he is talking about here the clockwise direction. So the encircled in a clockwise direction. Say for example, if we take one example to understand this, how we can study the stability. So G of S into H of S, if we have taken as 10 by S into S plus 1, So 10 by s into s plus 1, where the number of poles. See here, P is nothing but number of poles of g of s into h of s, which are located. This is very important. Number of poles of g of s into h of s, which are located in right half of s plane. Right half of yes plane. So this is very very important, this point, how the p is defined. So the p is nothing but how many number of poles, how many number of poles of g of s and h of s which are located in the right half of s plane. Means here s is equal to 0 and here it is equal to s is equal to minus 1. S is equal to minus 1 and 0, which will lies on the yes left of s plane only. So this is minus 1, this is 0, this is 0. Okay, so if it is s minus 1 is there here, s minus 1 in the sense s equal to 1, so that will be lie on the right hand side. So based on this statement of the p, so how many number of poles are lying on the right hand side, that we can say as 0. There are no pole is lying on the right hand side. So now from this, but we have stability find of n is equal to minus p. N is equal to minus p. So where n is equal to minus p means number of encirclements is going to be 0. That is Nyquist plot, which is going to obtained in the f plane. In the f plane, which will not encircle by the origin. So number of encirclements are here is 0. So it will not encircle. It will not. This is say f plane. So the plot which you are going to plot here, say for example, this is the Nyquist plot. So it is not encircled this new origin of f of plane, because there are no encirclements. There are no encirclements of the about the zero. Now, for making to understand better this, what we are doing is the stability criteria remains. We are going to keep the same. That is n is equal to minus p, n is equal to minus p. But p is, we are taking about number of poles which are lying on the number of poles which are lying on the right side, which are lying on right side. That is which you have taken. So this is also same, this is also same. That the change we are taking this here n number of encirclements, here number of encirclements about the origin we have taken in the previous days. So in order to make the better way understanding of this, we can say encirclements of a critical point. We are taking the critical point here. So critical point is nothing but minus 1 plus j0. So here this is what we can say critical point. The minus 1 plus j0 is taken as critical point of f plane. So critical point of which one? Of f plane, because we are taking about the f plane. By Nyquist plot, you can take it as by Nyquist plot. So what we are taken earlier, n is the encirclements of about the origin in the f plane. So rather than this, in order to study the stability in this case, we can't we can say either it is this side or this side, like this we can. So we cannot study about the stability. So for making better understanding, when the p is n is equal to 0, so better you can take the critical point. Better you can take the number of encirclements of the critical point, that is minus 1 plus a0. Then we can find the stability. So from whatever we take, that is the critical point, n will be taken for the encirclements of critical point. It's not the encirclement about the origin. Encirclements about the origin. So now generalized Nyquist path we discuss how the Nyquist path will be taken into, and its mapping also. Generalized Nyquist path and its mapping. So we'll discuss this. Yeah. So if the function has poles at origin or poles on the imaginary axis, So the f of s which you have taken maybe have the poles at origin, or the function which you have to take, the open loop transfer function also. You can take any function which you can have the poles at origin, or you may have poles on the imaginary axis as well. Poles on the imaginary axis. So in that case, Nyquist path cannot be selected along the imaginary axis passing through the origin. If it is having the poles at origin, poles on the imaginary axis. So here if it is like this, poles at origin and as well as poles at on the imaginary axis like this. So Nyquist path cannot be selected along the imaginary axis passing through this. Okay, so that's why what we are doing, we cannot say when it is pole at origin is there, then we cannot take the Nyquist path straight away from this plus j infinity to minus j infinity. We cannot take passing through this origin. Why? Because that analytic function will not be satisfied. That analytic function will not be satisfied. So that is why it should not pass through this poles at origin. So that this is because mapping theorem, what we are going to discuss, at every point it should be a analytic function. So if it's passing through this origin, then it is not a analytic function. So that's why in order to make this analytic function, that is f of s analytic function, this Nyquist path should not be drawn through this origin, That's what the Nyquist path is. So Nyquist path modified. How we are going to modify this? Then we have to bypass this. Means we can choose, because this has to be, Nyquist has to be chosen only in the right side. So this has to be taken, bypassed. Means without passing through this point, we are going to draw one more path like this. So that is a bypassing path. So from plus j infinity to minus j infinity, it is not passing through. It may pass through up to here and then very near to 0, then it will bypass it and then it will come in this direction and then move in this direction. So here when there is a pole at origin, we cannot show then we can say like this. Then we can say like, so the entire right half of this plane is covered, but this pole at origin, because of the pole at origin, we are bypassing this area from this point to this point and then joining to the minus infinity point and then closing this to the starting point. So okay, terminating point and starting point. So starting point is the omega is infinity, terminating point is omega is minus infinity. Okay, so based on this, Nyquist path has generated. Now, depending on the situation of the poles of g of s and h of s, Nyquist path we are going to select based on this one. So now the guidelines have given how to choose this path and all this. Say for example, even it will not pass through the this pole at origin. Say for example, there is a pole. This is about plus j infinity and minus j infinity, and I'll write one more. If we have one pole at origin and one more pole at this particular, say for example, minus j some omega 1 value, Say this is one more pole at minus j omega 1 minus value. Say for example, this is positive and this is a negative, omega 1 plus omega 1 minus. Okay, so at this particular point, if I have a Nyquist path, so that is starts from where minus j plus j infinity to minus j infinity. So plus j infinity. If I'm going to, so modified path I'm showing here, modified Nyquist path. If there are poles on the imaginary axis and poles at origin, if we have, okay, this is, say for example, I'll be taking this as j0, very near to, this is minus j0, and this will be taken as plus j0, okay, and then we can take it as one more point here. This is that is my j omega 1 minus. I have a pole at j omega. Say for example, this is j omega 1. I'm taking the pole. Okay, I'm taking the pole here. Okay, so here is also, I'm not taking the pole. Here is also okay. So I'll draw one so that it will be, I'll draw bigger so that it will be easy to understand. So this is 0. So I'm taking a point here, one pole at origin, and one more I'm taking at here, say for example, this is j omega 1 is the one point, and similarly minus j omega 1 I'm taking one point, see minus j omega 1. So this is minus j omega 1. So what Nyquist is suggested is, so from we need to take that starting point is plus j infinity. Say assume this is the starting point, and say we can take this is going to be the terminating point. Say minus j infinity, minus j infinity. So here it starts. The Nyquist path starts from here, and it will not pass through this point and as well as this point. It will not pass through this all these 3 points. It has to bypass at this particular point. So for that, what he has taken is, he has taken a point above this j omega 1, which is taken as plus j omega 1 plus. Means here this omega 1 plus means just above this j omega 1 value. So omega 1 is equal to 10 in the sense. So omega 1 plus value is nothing but say 10.5 or 11, like that. So just above that point. So up to that we need to show this Nyquist path like this. Okay, like this. Then the point which I have taken, that is omega 1 plus, and then one more point just below this omega, that is omega is equal to, omega 1 is equal to 10, then omega 1 minus will become 9 or 8, less than 10. It is less than 10. So this will become j omega 1 minus plus j omega 1 minus. So this has to be bypassed like this, and then it has to come like this. This is the arbitrary path or Nyquist path initially we are going to take, right? So next, so here if it comes to here 0, there is a pole at origin, so it should not pass through this point. So what I do is say 0 plus, just above the 0 value, up to that we'll show the Nyquist path like this. Up to this we'll show the Nyquist path, and then one more point will be taken as minus j0 minus, minus j0 minus. So 0 minus is nothing but a little lesser than value of the 0, little lesser than value of the 0. So like this we have a path. Now coming to this point, then I'll take one more minus j omega 1 plus, a point which is just above this minus j omega 1 value, and similarly I'll take one more point which is minus j omega 1 minus. So likewise I'll take this, so like this. Then here I have to bypass because it should be analytic. The f of s function should be analytic according to the Nyquist. So that is why it is not passing through all these points. Now it is come to the minus j infinity, and it covers entire right half of s plane, and it covers entire of right half of s plane. So in this direction, so it will terminate at this starting point. So this is about the Nyquist plot, Nyquist path in a s plane. So this has to be mapped to f plane. This has to be mapped to the f plane. So if you take this starting and end point, if you take this starting and end point of this, so say for example, the sections has to be taken here. The various section which you need to take. Say for example, this is from here to here is one section. So this is called section 1, and from here to here is section 2. Then from here to here is section 3, that is this point, like this. Then section 4 is this point. From here to here is section 4. Then section 5 is this one. This is section 5. Means from this point to this point, each points. Then section 6 is going to be from this to this. From this to this. This is section 6. Likewise, each section. Next, section 7 is what? This j omega 1 minus 2 j infinity minus j infinity. We can call it as section 7. Then section 8 is nothing but this entire thing will become as section 8. means from here to if you take from here to here, this is the entire thing is called as section 8. Section 8. So if you write all these points, that is section 1. Section 1 starting point. What is the starting point? Section 1 is plus j infinity. Ending point of this section 1 is plus j omega 1 plus j omega 1 plus. So what comment we can do is, this is about the along the imaginary axis. Along the imaginary axis, this section covers from plus j infinity to plus j omega 1 along the imaginary axis. Then section 2, what we can say here, starting point is plus j omega 1 plus. So the first section ending point will become the second section starting point. Second section starting point, and ending point of this is going to be plus j omega 1 minus. And what we can say from this, it is a semicircle radius of, we can take the semicircle radius of which is tending to 0. So here this one will be taken as a bypass from this. This is a semicircular region. So this is what we can say, semicircle region. So that is why this section have look at of semicircle region in the S plane of Nyquist path. Right. Similarly, third one is going to be starting point will be the second section. Second section ending point will be the starting point. So j omega 1 minus is going to be the starting point for the third section, and plus j0 plus will become the ending point for this third section. So what is this? Is also along the imaginary axis. Along the imaginary axis. Now fourth one is plus j0 plus 2 minus j0 minus, means it is from, it is semicircularism. Once again, this is a semicircularism. Next, fifth one, minus j0 to minus j omega 1 plus. So from this till this point, from this point to till this point, this is called as fifth section. So what is this? Along the imaginary axis only. Along the imaginary axis only. Then seventh section is sixth section is taken as minus j omega 1 plus, and the ending point is minus j omega 1 minus. That is the sixth section. So it is of course it is along the semicircle. This is the semicircle here. So it is a semicircle. How the path is going to be here? Along the semicircle. And also seventh one, if I take here the section is minus j omega 1 minus, then this is going to be minus j infinity. So minus j infinity. So it is along the imaginary axis. Along the imaginary axis. Then eighth section, if you take, it is from minus j infinity to plus j infinity. So it is entire the right half of S plane. So this section 8 is entire of the right half of S plane from minus j infinity to plus j infinity. So this is about each section, how it covers in the F plane. Now mapping of these sections, all these sections which I have discussed here, 8 section has to be mapped in the F plane. So mapping of these section in the F plane, how we are going to achieve this? Because this is S plane, so you need to use the mapping theorem and convert all these S points into the points on the F plane, S points into the points on the F plane. Then we have to get the Nyquist plot. So how we are going to get this is by using the, here the polar plots are going to help us. Here the polar plots are going to help us in order to draw the plot on the F plane. In order to draw the plot on the F plane, polar plots are going to help us in mapping of these S points and the F plane. So how to do that? That we will explain here. So we have taken that function, say for example, the function which I have taken as say g of s into h of s, okay? And if frequency domain, how it can be written as g of j omega into h of j omega. And for the section 1 which you have discussed here, it is plus j infinity to plus j plus j infinity to, what is the section 1 here? Starting point of the section 1 is plus j infinity to plus j omega 1 plus j omega 1 plus. So we'll study for section wise. Now for section 1 we have 2 points. One is starting point of the section 1, which is s is equal to plus j infinity, that is nothing but omega is equal to infinity here, and terminating point, we have terminating point, that is j omega 1 plus. For the section 1, s is equal to plus j omega 1 plus. It means that omega is equal to some value omega 1 plus. So here you need to get, in order to get the magnitude and phase angle. So how you did in the polar plots, we are going to find out the magnitude and the phase angle for the different values of omega. So here the omega is infinity. Substitute the omega infinity in the magnitude of mod of g of j omega into h of j omega, whatever you get the magnitude. This is what you can say magnitude. And the phase angle is nothing but angle of g of j omega into h of j omega. So substitute these omega values. Omega is infinity and find out the magnitude, and omega is equal to omega 1 plus and find out the magnitude and the phase angle. So we know we are going to get the points, the starting point and the ending point, and also in the at the end we can say that is rotation of the plot. So rotation of the plot we are going to take like this, because from the terminating point, what is the phase angle you got? Minus of, that is yeah, infinity, that is the point which you have got infinity, pi of infinity minus pi 0. So that will give the rotation of the plot. So if it is a negative direction, if it is a negative angle you got, that is in a clockwise direction, we have to rotate the plot, and if it is a positive, then we have to rotate the plot in the anti-clockwise direction. So that is what we can obtain from the polar plot. Likewise, so the rough curves is going to be drawn mapping the section this in the F plane. So after finding this and this, we need to draw the rough curve on the F plane by using these 2 points. Now for section 2. So section 2, we'll write the section 2 here. Once again, we find the starting point and terminating point. Okay, so terminating point, then we'll find out the magnitude, then we'll find out the phase angle, then rotation of the plot as usual. So for the section 4, now we have done similar to the section 2. Also we have to do the starting point, we need to find out terminating point, we have to find out at that particular omega value, find out the magnitude, and the phase angle, then rotation of the plot. So this is, once again, we need to draw the rough curve on the F plane. So after mapping all these sections like this, we'll get a closed plot called Nyquist plot. So after mapping, means for each section we are getting the single polar plot. So if you combine all these plots, then we can get a closed plot called as Nyquist plot. So after mapping all these sections, we will get a closed plot called the Nyquist plot. Now after drawing this, now we have to count the number of encirclements of the critical point -1 plus j0. This is very important. So we need to count the number of encirclement of the -1 plus j0. So we need to locate the -1 plus j0 point. Then from that point you draw in any directions and then count the number of encirclements. Okay. So if it satisfies this condition, n is equal to minus p, that is number of encirclements is equal to the number of poles, that is which you have discussed in the just Nyquist stability criterion, that is number of poles of g of s and h of s which are on the right of s plane. So this p we are going to find out if it satisfies this condition, the number of encirclements is equal to the minus p. So we need to find out this. So here, if you look at this, one more very important here is there are sections will be mirror images of section C, 5th and 6th, 7th. So if you look at this, here. So these fifth and sixth and seventh are the mirror images of section 3 and section 2. I mean, fifth is mirror image of 3, and sixth is mirror image of 2, and seventh is mirror image of 1. Seventh is mirror image of 1. Mirror image of 1. So once you find out the section 1, section 2, section 3, then it is enough. Need not to find out the fifth and sixth, seventh. We can draw mirror image of that. So up to section 4, we need to find out. Up to section 4, we need to find out. That is remaining. That is fifth, sixth, seventh. Need not to find out. Need not to find out. Okay. That will become the mirror image. And finally, the eighth section, that is last section, which is from minus j infinity to plus j infinity. That is the last section which we are going to discuss. That is here. Omega is minus infinity to plus infinity. Omega is minus infinity to plus infinity. To plus infinity. So when the starting point is minus j infinity and ending point is plus j infinity, where we can take is omega is minus infinity to plus infinity. So magnitude of this is going to become 0 for both starting and terminating points in this case. If I substitute the magnitude, so it will become 0 for both the cases. For both the cases. So 2 points coincides at origin. So magnitude coincides at origin. Magnitudes of these points will become 0. So that's why these 2 points will coincide at origin. So there exists some rotation about the origin with r tends to 0 before plot the terminates at origin. So these rotations will not affect the encirclements of minus 1 plus j0. So the rotation which you are doing here for this omega values will not affect the encirclements on minus 1 plus j0, as these encirclements is almost 0. So that's why it will not encircle. It will not encircle the minus 1 plus j0, because which is exactly this origin. It is going to end at this particular point origin. So minus 1 will become here. Minus 1 will be here. That is minus 1 plus j0 will be here. So it will never be encircle this minus 1 plus j0. For this, omega is minus infinity plus infinity. So in this, what we are going to stability analysis is going to do is to show the mapping of last section as a single point, that is origin. There is no need to show the analysis for this last section, that is minus infinity to plus infinity, minus infinity to plus infinity. We are not showing this in the F plane. Why? Because it will be at origin. That whole thing which I have shown in the S plane, the whole thing which I have shown in this S plane will become, this is S plane, will become a point in the F plane, a point in the F plane for section 8. That's what I want to consider. So joining all this, once you do all these things, joining of all these polar plots of all sections, one by one, the mapped locus we can call it as Nyquist plot. The mapped locus we can call it as Nyquist plots. Now, so stability, what we can say, because number of encirclements is equal to n is equal to minus b, then we can say if it satisfies that condition, we can say the system is stable. Now, how to calculate the gain margin, phase margin from Nyquist plot? It is similar to the calculation of GM and phase margin which you have taken in the polar plot. So polar plot, how we have calculated? How we have calculated the gain margin and phase margin, okay, and frequencies, gain crossover frequency, phase crossover frequency. All this will be calculated by using how you have done in the polar plot case. So now here I'll give the steps how to solve the problem by using Nyquist criteria. So here the steps I'm going to discuss here. Steps involves. So first one is we now count. First and foremost thing, n we are a p we are going to find out. P, that is count how many number of poles. Count how many number of poles means nothing but we are finding the p value. How many number of poles are lying in the right half of a spleen. This is the first thing. That is nothing but what we can say from this. It's nothing but we are going to find out the p value. P is how much. Second one, decide the stability criteria. That is, we know that p, once you get the p, n is equal to minus p. That is the stability criteria. Stability criteria, that is n is equal to minus p. How many times the Nyquist plot should encircle the critical point? That is what we are going to study here. So decide the stability criteria, that is n is equal to minus p. So we need to find out how many number of encirclements about the critical point, so that we are going to find out. Next, third one, select Nyquist path as per the function. That's what we have done now. Select the Nyquist path in the S-plane. So Nyquist path in the S-plane, we need to find out as per the function, So what we need to see here in this case is very importantly in this case we need to see is whether pole at origin is there, or any pole on the imaginary axis are there, So these things we need to check out in this third point. That is, select the Nyquist path as per the function g of z. So we can select if there is no pole at origin, then straight away we can take like this. Okay, this is the point, starting point, and plus j infinity minus j infinity, and then we can show the path like this along the imaginary axis and close this. But if there is pole at origin, as we discussed just now, we have to bypass the path without passing through that particular pole at origin, so that we can get like this. So that is the third step to decide. And then fourth one, is once you find out this has to be divided into sections. So analyze the sections. As starting point and terminating point of plot. So last section is not required because it equal to the zero. That is at origin. So the last section in the polar F plane, if I convert that, it will become 0. So that's why last section is not required. So analyze the each sections. So means section 1 and so on, 2 and so on. How many sections you have got? Each section has to be find out that starting point and terminating point, and then plot it. Then second section, starting point, ending point, you need to find out, then plot it. So all these combined plots will become the Nyquist plot in the F-plane. Okay. So next step is fifth one. We can use the determining of mathematically find out the omega PC. That is, we have discussed, that is how to find out the omega PC. Rationalizing, that is mathematically determine the omega PC. That is the fifth step. That we can do rationalizing of the imaginary part with the imaginary part, because on the real axis imaginary part will become 0. So that's why we can take the omega PC, which crosses the minus 180 degree line, means this is the minus 180 degree line. So on this line, this is the real axis line. So on the real axis line, imaginary part is 0. So equate the imaginary part to 0 and then find out the omega PC. Then sixth one. So using step 4, that is sections, and step 5, that is intersection point we need to find out here. Omega of PC is nothing but where it exactly intersect the minus 180 degrees line. So that is nothing but intersection point, which gives the intersection point with negative real axis, with a negative real axis. So that point will give the omega PC. That point will give the omega PC. So using step 4 and step 5, we are going to sketch the Nyquist plot. Sketch the Nyquist plot. So now last step, we need to find, after sketching the Nyquist plot, we need to find out the number of encirclement of -1 plus j0 critical point by the Nyquist plot. Suppose if it is matches with n is equal to minus p. Suppose if it is matches with n is equal to minus p. If n is equal to minus p, system is stable. Otherwise, system is unstable. So these are the steps which we have to find out. So gain margin, now we can find out, of course, by using, we know that Q is the intersection point of with the negative real axis. That is what we have told here. This is the where the intersection point I told you. This is the intersection point is nothing but Q here. So gain margin is equal to 1 by mod of OQ, means from the origin to the Q point length. Then Q is, as I told, that Q is the intersection point with the negative real axis, or if you want in terms of decibels, we can apply 20 log of 1 by mod OQ will be given as in decibels. This is about the Nyquist plot. So this has to be, once you understand this procedure, then it will be easy to construct the. So in the next class, we discuss one problem on this Nyquist plot so that we can easily understand. So today we'll stop here.